let's record. Short announcement is that after this session, I'm going to be doing a practice talk for my talk at WITS next week, which is a workshop for workshop of implementation type systems, which is looking at practical problems. And I'm going to be talking in particular about the standard library and design decisions in the standard library. So if people are interested in that, feel free to stick around for 10 minutes. It's only a 12-minute talk, unfortunately. So feel free to stick around after the...
Okay, Matthew, I would love to hear that. I've got a 2:15 meeting, so maybe there's just time to squeeze it in, but...
Yeah, cool. Otherwise, I guess we can get going.
There's one more organizational issue, and that is that it seems that we're going to have more and more seminars on Fridays, and it probably means that if we want to keep up Agda meetings at a reasonable pace every other week, let's say, we should probably decouple them from the seminars, and that means finding another time slot for these. And I see it might be tricky for some of us. So I don't know if we want to try to think about it right now or sort of offline, but this is probably something that's going to happen. Because in 2 weeks' time, we have a seminar scheduled already, and it's not going to be any easier after that, I don't think.
Would Thursdays at 1 p.m. work for people?
Probably.
No,
a provisional yes.
Predators are saying no. Well, let's go through the days. Would Monday, Tuesday, Wednesday at 1 p.m. work for? Which days can people do?
Yeah, I think Katya's right that we should probably take it.
Yeah,
we'll
put up a poll.
Yeah.
Yeah. Okay.
Okay. All right. So, which chapter should we look at today? I think it was equality and equality reasoning.
I think we ought to. Did we finish that? Or did we go up? Were we on isomorphism? No, we weren't.
No, we definitely didn't look at equality. We looked at equality because we sort of skipped ahead. We didn't look at the chapter. We did look at the implementation, but not at the chapter. I don't think so.
Yeah. I had a question right at the beginning of that, so that would be great.
Yes. Okay, perfect.
Yeah, go for it, Paddy. What's your question?
So I missed the last session, so I may be asking things that would have been clear if I'd been there. But in the paragraph headed equality, it says the definition features an asymmetry in that the first argument to infix equals is given by the parameter x:(a), while the second is given by an index in A arrow set. This follows our policy of using parameters wherever possible. The first argument to equals can be a parameter because it doesn't vary, while the second must be an index, so it can be required to be equal to the first. But I did a bit of searching. This appears to be the first occurrence of the word index in this book. So I feel justified in not knowing what on earth that's on about. What's an index?
So maybe let me share the screen for that.
Who's feeling brave to explain this?
The short way of explaining that, I think, and correct me if I'm wrong, Matthew or James, is that when we have data definitions like here, right? We have data, the name of the data type we're trying to define, and then the stuff here, right? And the last of these is the sort where the data type will be living. In this case, the space of all types, right? The set here.
Yeah.
But if we check the type of the equality, like it's written here, it will say something like for all A of type set, A arrow set.
Yep.
Yeah. So now the thing is, there's two kinds of these arguments. And we can see both of them here, right? There's the ones that we are naming already here, and the ones that remain, so the ones that come before the colon and the ones that come after the colon.
Okay.
The ones that come before the colon are parameters, the ones that come after the colon are indices.
Oh, as simple as that. Okay.
Unless I'm wrong. But I don't think I'm wrong here.
Okay.
And so
thank you.
It's a bit tricky because they behave differently, in the sense that there's certain things that you're allowed to do with indices that you're not allowed to do with parameters. But on the other hand, parameters give you, I think they give you nicer induction theorems or something like that. So that's why if we could say data equality is of type colon, right? So move all the parameters to the right-hand side.
Mm-hmm.
And then we wouldn't have A or X in the scope for the constructor definition. Note that here, this X is the X that we've introduced here.
Yeah.
So the parameters are sort of already in scope for all of the constructors.
Okay.
So,
Right.
so that's quite an operational reading of these things.
That's true.
Let's step back and offer a conceptual reading. Is that parameters to an inductive family really are, as it were, things that homogeneously vary. We are defining for all A and for all X parametrically the family of being equal to X when X is of type A.
Mm-hmm.
And that definition, so as Philip says, A and X are in scope at that point. That definition is then prescribed by offering constructors to witness elements of that family. And that family is then offered in the index part, the right-hand side of the colon, as a family of types over A. So the second argument, here the second X, is as it were something which can vary heterogeneously, or at least non-homogeneously. So we're not picking out all the possible A's, we're picking out this special one, which happens to be the same X that's already in scope.
So could I say, conceptually, those two lines there are shorthand for an infinite collection of different equality definitions, each one being equality for a particular A and a particular X.
Yes, but that infinity is kind of homogeneously or parametrically described once and for all.
And that's why I can replace that infinite collection of declarations by the two lines that I've got here.
Yeah.
Yeah. Okay, thank you.
But you could imagine in other contexts, and this is where it's worth going back and looking at things like less than or equal to on the natural numbers, is where you see the indices in such a type family actually vary from constructor to constructor. And one of the things that's happening here is that we're specifying via the parameters that A and X will always be fixed throughout all the constructors of this type family.
Mm-hmm.
But there is only one, so it's harder to observe that distinction.
Yeah.
But we could imagine, suppose A was a set that actually had an inhabitant, little a. You could write down a type whose only constructor was parametric in A and X, but then announced that it was going to be the predicate that was always the case that X was equal to a little a.
Yeah.
Okay, so as it were, you could anchor in the index position particular shapes of allowed inhabitants, or rather families allowed to have inhabitants.
Okay.
And it's that inhomogeneity of the indices which allows you to describe, as it were, good old-fashioned inductive definition or inductively defined relations, where the elements varying actually vary. So indices, as it were, are things which can vary from constructor to constructor, whereas parameters are things which are held constant for the definition.
Yeah. Okay.
Almost.
Almost.
Recursive calls, right?
Yeah.
Parameters can vary on recursive calls.
Yes.
But yeah, and I'm not sure how that sort of matches that intuition of homogeneity. No, I take your point. Although I think this is sort of related to the nested, like if you think about the parameters as the sort of standard parametric part of the definition, in a sense, then it would maybe be somehow related to some of the nested types that you can encounter in functional programming, right? Where you still allow something to change.
Yes.
Between like in the recursive calls.
So the soft analogy with data types in functional programming is that the parameters can change subject to whatever your usual intuition, I don't have one, is about so-called polymorphic recursion. Whereas the index variation is much more like the phenomena of generalized algebraic data types, GADTs. So if you're familiar with GADTs, then one way to think of the index positions in type families is that they are like the non-parametric variation in GADTs. And the parametric variation, the variation in the parameters, is more like allowing polymorphic recursion in data type definitions in, say, Haskell. And Joe might be a good person to tell us another time about polymorphic recursion and the fact that if you don't have any type annotations at all, then you rapidly get into issues of undecidability. Whereas the fact that we're being extremely explicit and passing around the types we think things should have, we're able to check polymorphic recursion rather than infer it. But that's a big parenthetical digression, so apologies for that. One way to think of equality is that it's a relation like anything else. So it has some stuff that stays the same over the family of definitions, and it has stuff that varies on a constructor by constructor basis. And they're the analogy with less than or equal to or whatever on that.
Yes.
Helps. But of course, this is a very, very, very special relation because you have X on the one hand and X on the other. And so when anything type checks as being of type blah equals blah, the type checker either knows or will complain that it doesn't know that those two things really need to be definitionally equal.
Well, that's if you have a REFL proof. That's if you provided REFL as the proof, right?
Indeed, indeed. But if you have a hypothetical proof that X is equal to Y, modulo other considerations of higher structure, which will not detain us in this reading group, that proof can be pattern matched on and must be the only pattern which matches a proof of x equals y is REFL when y is actually definitionally equal to x. That's how rewriting and the kind of Leibniz-Bentham identity of indiscernibles idea comes into play. When I know that two things are equal, I really know they're equal. I don't just have a proposition that's sort of lying around, not able to do work for me. I know that any argument to a function of type x equals y can be matched against the pattern REFL.
Yeah.
Matthew, you look concerned.
No, but I mean, that makes sense to me. It took me about a year, I think, of using Agda seriously to actually kind of intuitively grasp what this definition does. So if Natalia and Marco, if you're a bit lost about the theoretical discussion about this, that's absolutely fine.
But let's also say that feature of equality is in a sense not special, but is part of the machinery of pattern matching. When we do induction on an inductively defined relation, when we match against the various constructors for that relation, or a richly dependent data type, the type checker is forcing the indices of that type family in each of the cases of the patterns to actually definitionally conform to the specified forms of the definition. And it won't always be able to do that.
Yeah, sometimes it will die.
So if I have a type family in particular which mentions a defined symbol like plus or if then else, then for the type checker to do pattern matching against such definitions, it would essentially be having to say, I hold an index in my hand, which I know to be definitionally equal to the value of a defined function symbol. And that would be tantamount to inverting that function, which in general, we know we can't do. And in practice, we never try to do. So having function symbols appear in index positions in constructors of inductive families is a big no-no. And it's a sufficiently big no-no that it has a meme associated with it that is called green slime. It's called slime because it's unpleasant and infects everything. And it's called green because that was the color assigned originally to it in the definition of epigram 20 years ago. So yeah. So the motto is avoid green slime at all costs. But in terms of nurturing the Agda type checker, that means don't ask the type checker to solve unification problems that you know it can't solve when pattern matching in goals.
Yeah. So one thing that is probably important to note here, compared to some of the other theorem provers, some of us will definitely be familiar with, is that equality is in no way baked in, right? This sort of propositional equality, this guy, it is just a definition. And like James said, it's the mechanics of pattern matching that give it the behavior of equality, the behavior we sort of expect of equality, right?
That's 99% true. I mean, the observant people might notice that somehow, but rewrite only accepts, rewrite, which is or rewrite only accepts these propositional equalities, and rewrite is a built-in keyword. So in practice, you can define, you can tweak this definition slightly. You can play around with indices and where the parameters live and whether you quantify over in the REFL.
The rewrite is just syntactic sugar. You can write the direct width.
Yes, and width does not care about equality.
Yes. Okay. my point stands. There's other features that do assume properties of propositional equality, and you hook it in when you declare it. You have to hook it into in order to use those properties, you have to declare that this is the notion of propositional equality that I'm using, and then that hooks into Agda's, hooks into some of the internals of Agda. That makes
sort of like natural numbers is just a data type, but we can
hook it to Haskell.
Hook it in so that either Haskell or numerals.
What would be a quick list of those features? Rewrite, obviously, because we were discussing it, is directly hooked to the propositional equality. What other features? What's the top 5?
So there's set of modules called Agda built-ins. And in the main Agda repo, not in the standard library or anything, and that all the hooking is confined to those 5 modules or 6 modules, or maybe it's grown since I last looked, but where everything that is hooked in there, and the special rules for those modules apply. Things like safety. If you're trying to mark your proof as safe, so not use any unsafe features of Agda, then safety checking is disabled in those core built-in modules. I can find them for you after the talk and send them to you if you'd like.
Not urgent. I just was wondering if there were some obvious syntactic features which were directly tied to, in the way that the rewrite syntactic sugar is directly tied to that type. That particular data type.
Yeah. So another one is not congruence rule, confluence. What's it called?
Congruence.
Not congruence.
Oh.
It's like rewriting, but it is, you can declare it in a pragma and it will automatically reduce things for you.
Yeah, that is called rewriting, but
that's called
rewrite.
Yeah, that's rewriting. That's what I. Yes. Sorry.
So there are 2 different notions of rewrite in Agda.
Yes. Yeah. Yes, there are rewrite. So that's what I was. Sorry, that's what I was talking about when I said rewriting. Which, yeah, I'll send you a link to it afterwards. Let's not get tied into it. But.
Right. So, I suppose once we've defined our equality, right, we have the proof of reflexivity of this relation for free, since the constructor is it. Right, the type of the constructor, if we just check its type in Agda, will say that for any type and for any element, it's equal to itself. So we know that the relation is reflexive. And so in order to show that it's an equivalence relation, we then have to prove symmetry and transitivity, right? So this is what the book does next. So is there anything interesting happening here? Oh yeah, here we see an example of what James was talking about, right? Here where we look at the, like we try to define symmetry, and what we do is we look at all the things, all the ways in which the original proof that we started with, that x is equal to y, could have been defined, right? And since there's only one constructor, it has to be the reflexivity. And what happens here is that one of our variables disappears. Right? We lose y and get a dot before the x.
It sounds as though you're typing something, but we are not.
That's unfortunately me.
Oh, okay, fine. Just.
Sorry, no. Yeah. And so for transitivity, we do virtually the same thing, right? We establish that both the first equality had to be constructed by reflexivity, so the two things had to be identical, x had to be identical to y, and then do the same thing for y, which we know is x equals z, and we get that the only thing we have to show is that x is equal to x, and this, of course, we know how to do, it's reflexivity.
Can someone explain the notation in those boxes? Because it seems like some of it is stuff that you're supposed to type into the file and is going to run, and some of it is just comments, and I can't quite tell which is which.
All of it runs, so you can copy and paste it in and run. The dashed line is the only bit that I wouldn't add. That is literally a comment, because
Okay,
two double dashes, sorry, a double dash starts a comment.
Yeah, but
to
okay,
distinguish.
so now I understand. I just have to remember that that's a comment, and
yeah,
it's ignored, and it's just someone trying to make it look.
Pedagogically, yeah.
Yeah.
yes.
Okay.
So the blue boxes are what's code. The purple boxes are, or lilac or whatever, are the response, right? So this is what you'd see in a goal.
Thank you very much. That's very valuable information.
Yeah.
The color coding was not obvious.
Yeah. So yeah, and this is also why you don't get syntax highlighting, because it's the purple ones are not really checked by Agda in any way, right?
Yeah, I believe that the blue ones are actively checked.
Yes.
As part of a process of generating this web page.
Yes.
So
if you go to the Agda source, the .lagda.md, then indeed you can process that with Agda, and I get all done because there are no open goals. And that's because in terms of definitions, everything in this file is actually complete. Trans is declared with a type and fully defined. Sim is declared with a type and fully defined. But the goal reporting, etc., is not actually checked material. That's pure commentary.
Yeah. I don't think there's a way to hook into Agda with this sorts of things, right? With just checking, just in order to check that the goal is what's.
It would be a good student project for someone to generate those from running the code.
Yeah, but the problem is that once you have this code here, you don't get that. You do get these responses is what you get in the process of refinement.
So the student would have to have a way of embedding the partially completed stuff and generating the response, but not actually showing the partially completed stuff.
Sort of, because the partially completed one, this is the partially completed one, and you can see that it's in a purple box, so it's sort of, it's not checked, it's like a response, but it's not a response, it's a definition. It's a partial definition, it's a definition with a hole, and then the refinement of this hole by pattern matching on E on the equality, which gives you this, right? And with this goal is how you refine that. So I think Phil was well, complaining, I suppose, a little bit about, this being the one part of PLFA not checked because there's no real way to hook into the system.
You could do it because you could define some syntactic sugar to introduce in a local module to disambiguate with different sim definitions, and then you could turn off warnings for holes, for empty holes. So
yeah, but
But what you have here is a mismatch between the temporal ordering of the type checker's processing of user gestures and the static ordering of dependency of definitions within a given file as a complete, declared and checked object.
Yes.
When you work with tactic-based theorem provers, there's generally a smoother integration conceptually between the execution of a tactic and the diagnostic reporting of its output, because somehow those things are synchronized. But here, because we're really observing the end product of a completed set of gestures towards type checking a complete file, there's as it were no means to record the history of how we got there as snapshots. It's a kind of overlay problem, which is slightly the opposite to the stateful overlay problem you get in things like Jupyter notebooks, where you can get the notebook into an inconsistent state by repeatedly evaluating expressions which change the content of the notebook. Whereas here, this is intended to have a purely declarative reading, and hence it's a bit harder to capture some of those more procedural aspects, let's say.
Yeah. All right. So we go on. We've checked that it's that we have an equivalence relation, right? So what we do further on is we check that equality behaves like equality, in particular that it's a congruent, right? So, and here we see, well, basically two instances of NRE functions being congruent, right? So if we have x equal to y, then for any f x is equal to fy, and we can have a version of that for any number of arguments. And more importantly, because that really behaves the same way as the proofs we've seen before, and there's not really very many ways in which it could have differed, right? Because what else are we supposed to do? We have to pattern match on the equality. We have nothing else to go on. And after we do that, we're left with identical objects, right? So the more interesting bit is probably this one, where the equality of the functions we can also pattern match on, and we still will get just one function, right? It still will say, oh, okay, in this case, the second function must have been identical to the first function, definitionally equal, and so we basically just do the same thing. We're left here in this goal after pattern matching on the equality of functions. We're left with some function applied to x, and we're supposed to show that it's equal to itself. So again, REFL. Yes.
Are all our viewers following and happy?
Reasonably happy.
So in some sense, I suppose, you could argue that Cong2 is derived. Can you see it as such? Well, maybe not derived directly, but
are you saying you could get it from Kong and Kong app?
Almost. You could get it from a Kong that allows for equality on both functions and arguments.
Yeah, you could imagine a statement that puts together Kong app and Kong. Say if f is equal to g and x is equal to y, then fx is equal to gy.
Yes. And then Cong2, you would just use that twice with reflexivity on the function position in the end, right? Because fu is a function and fx is a function. And so once their arguments are the same, you'll be done. And yeah, we probably wouldn't even need that. Yeah, so I suppose that's a sensible exercise to figure out how to derive Cong2 from the other things that are already defined here.
So that also means you don't need a Kong n in general.
Well, you don't need it, but so the question then might be, why do you want Kong 2?
Or because
And
it's quicker to apply.
It's much nicer than trying
But then you can
to
define it in, but you
Kong
could
app.
define it in terms of Kong app and Kong. Right?
Yes, and the question is, well, you can't define it just using Kong and Kong app because the functions do not match and the arguments don't match. So you'll need something else that we already have. So Kong app requires that the argument matches, Kong requires that the function symbol matches. And here, neither the functions, which differ fu and fx, and the arguments v and y. So if we don't want to pattern match, don't want to define it by looking at these proofs directly, then we'll also need transitivity, right?
So the point you're making is you're trying very hard to avoid using trans.
Well, I'm not. I'm saying if you don't want to pattern match explicitly, if you want to define Kong2 just as a derived rule from everything else that we have, then you'll also have to use trans.
From the point of view of, practically using it to prove something, practically using Agda to prove something complicated, if you can match on REFL,
you should match on REFL.
Always match on REFL, because it simplifies your proofs unbelievably.
Yes, it basically makes half the arguments go away, right?
Yeah.
Yes.
Which is why I think is why they're encouraging it, is why they're writing it in this style.
Oh, certainly. Yes.
Yeah.
Yeah. So the final example here is is subst, which is almost like Kong, but with a slight difference here in the symbol position, in the operator position, right? We have P instead of F, and the type of P is not A arrow B, but A arrow set. So for type constructors, we can turn one type constructor into the other type constructor. Well, type constructor at one index into type constructor at the other index if we have x equal to y. And again, this basically works by pattern matching on the equation and on the proof of equality, and that means that we have what we wanted all along, right? Yes, and this I think we looked at before when we tried to figure out how these things work, right? How the equational reasoning works. So I think we've looked at these definitions in one of the previous meetings quite extensively. Yeah. So if there's any questions, just interrupt. Yeah. So I think these examples we've also looked at before. Yeah. And so, and that I understand that this is basically Agda practice for those at least who like these sorts of reasoning with chains of equalities or other relations. You can define these sorts of modules for all sorts of relations. Equivalence relations, orders, it doesn't really have to be anything. Well, okay, usually it will be either ordering relations or equivalence relations, but you basically can just go over these definitions and build them for your relation of choice, right?
The standard library also has some quite nice functional pipeline reasoning of the same style, where you write your types on the left-hand side and then your transformers between your types on the right-hand side in exactly the same left, right, or interleaved style, which helps when you've got a very long pipeline of functions. Helps you see what you've got at each step, the type of the thing you've got at each step.
Yes. Yeah. And then here we're using the rewrites, which is like what Joe was talking about earlier. So the syntactic sugar for using a lemma that proves some equality and just transforming the goal from left-hand side to right-hand side. Yes. More rewrites. Yeah, and here are the with patterns to which the rewriting is desugared. So personally, I don't think I've ever used the rewrites. I'm not sure they were there when I first learned Agda. And so I was almost always using the with patterns for that. And this basically means that you can, yes, name additional sort of let bind locally additional arguments and pattern match on them. So this is what happens here. We're saying, okay, I'll name the m plus n, and I'll name the proof of commutativity for m and n. And here I'll put my names. And then after putting my names in this line, I'll pattern match on them, well, on the proof here, and it will be a reflexivity proof, because that's the only way that equality can be constructed. And so,
am I correct in understanding that a dot pattern is essentially a syntactic sugar for a bound variable that's never referred to anywhere else?
No,
I don't think so.
So an underscore means bound variable, but it's not for anything else.
Well, the thing is, when I was experimenting with this, you could just put a bound variable there and just not use it, and it would.
Yes. So dots used to be. So what a dot means is that the unification forces that argument to be that expression, right? So the fact that you pattern matched on REFL has forced, what the dot denotes is that it forces that first argument to be n plus m.
Yeah.
Right. In about 3 years ago, Agda removed the need to actually write the dots at all. And you don't need to write the dots to denote that they're forced to be that. Agda can now infer that they're forced to be that because of REFL. And therefore you can just omit them entirely. And indeed, I'm a little bit surprised that they still have this in PLFA, because they're no longer necessary at all. I'm not aware, maybe James will correct me, but I'm not aware of any place where they are necessary.
So you can just put an underscore there right now.
You could put an underscore there right now. Indeed, yes.
Okay, so it doesn't give you any strength now, but it used to.
It used to. It used to be necessary.
Yeah, I think the split tactic still inserts them if it forces something. So that may be why they're here.
Yeah, some of the old machinery that automatically generates code might still put them in. You're right. Yeah.
At any rate, this is a sort of useful reminder that this is, basically what happens is we've forced somehow m plus n to be definitionally equal to n plus n, which is what we wanted, right? We wanted to look at this proof that m plus n is even, treat m plus n as the argument to the commutativity, right? This is what we are trying to do here, to sort of grab the m plus n, treat it as as something, as the left-hand side of some commutativity, and then by pattern matching on the proof of commutativity, we learn that this thing was in fact n plus m, And this is what gives us the fact that the type of ev, which used to be like that, is in fact what matches something that matches here, right?
And it's worth saying here, this is because we're working in a dependent type theory. If we worked in a simple type theory, or even a functional programming language like ML or Haskell with quite fancy types, nevertheless, the argument positions of a function defined by pattern matching are in principle independent from one another. But that is not so here. The rightmost argument of an n-ary function, the values that it can take as patterns, also constrain the preceding n-1 arguments of the function. And that bites hardest for indices rather than parameters, because you really get the choice of index also affecting further to the left the arguments of the function. So we see that here. The last argument position, this equational proof, as we pattern match on it, it changes the other argument positions of the function. In particular, m
Thank you for that. That's very helpful.
Yeah, and the type of ev.
Yeah.
Which is the important bit, because the whole thing we're trying to do here is change the type of ev so that it matches what we want it to be.
Yes. So actually, to loop back to subst, I might have made the following observation about the proof of subst, is that it's taking a term equation, a term equality, and lifting that up to a type equality. When we do subst, we have two types, px and py, that somehow morally are not comparable. But if I know that x is equal to y by virtue of reflexivity, then I know that the types px and py are actually the same type. And hence an argument ev or proof of type one of them will type check as being of the other one. And in a sense, it's a sort of perversity of functional programming notation. But this is where you can say either it's a perversity or thank you, the type checker, that Philip's point that in this proof of even com, in the course of all that pattern matching, the type of the argument EV has changed. But you don't see it because all you see is the bound variable name EV. You don't see its type changing. But
also it didn't really change. You could give the type, well,
yeah, that's an interesting, interesting quibble. But
you just know that they're definitionally equal now, so you can use either.
Exactly.
It's just that the type checker will happen to use the one that's it thinks is a normal form.
Yes,
indeed.
Sort of the one that you're asking, the one that it needs here, right? So the one that's written down here in this case.
But it could equally well rewrite that to the first one.
Yes, but it doesn't think probably that's not what it's going to do.
Yeah.
If you put rewrite of sim of com of n plus n, then it would rewrite it the other way around, and then you'd have it would rewrite the goal type to match the input type. So if you flip the direction of the equality,
and you then wouldn't see that at all in the program term, because the preceding argument would remain m plus n.
Yeah.
It's simply that the type of ev would have changed.
Yes.
So that's an important thing, is that rewrite affects both the goal that you've got and all the things that you have in scope as well.
All the types of the arguments in scope. Yeah.
Can you rewrite just in one, just in the goal or just in the argument?
Occasionally, no, you can't. And occasionally that screws you over massively, because occasionally you want to rewrite in the goal, but if you rewrite in your arguments, then suddenly your arguments start reducing. Your rewrite triggers a massive normalization in your arguments, and then your arguments no longer match the form which they were before.
So you may have made things equal, but the compiler won't know.
Exactly.
Yeah.
And that's the source of the agony that you see from time to time in the standard library comments and on Zulip about, I've got the dreaded not equals W problem.
Yes.
Yeah. We've only been doing this for 25 years and it's still hard. Yeah.
Which is, I guess, so it's 2 o'clock now.
Yes.
A tragically short excerpt of the book to have got through.
Yes.
But a nice way of kicking off the new year, I think.
Yeah.
Page everyone back in with the only type that matters. Because the other thing to say is pattern matching is nothing without equality. Equality is nothing without pattern matching. If you didn't have pattern matching, you could reduce everything to this relation and deliberate manipulation of it in terms and types. But fortunately, more than one person has written a PhD thesis so that you don't have to.
I'd like to express appreciation for all of you running these sessions. I'm finding this really interesting and really useful. So much appreciated. Thank you, everybody.
I found it very helpful as well. It may have seemed like you were discussing getting through almost nothing, but I found the inside information about what's going on in Agda very helpful.
Yeah, so I think, we're basically going through the book very slowly, but that is because the book is basically a jumping off point for James and Matthew and me a little bit too, right? And it's like we walked through a lot of this file ahead of time by just looking at the implementation of equality, right? So, and yeah.
And for those of us who've been around a very long time, it's very nice to have reached a point in history where these things can be sort of plain on the table for people to pick up, rather than having, you can buy machine-made cutlery from the supermarket. You don't have to dig your own iron, make your own steel, build a foundry to cut the forks and knives. But some of us who were there during that period remember what we learned doing so. And it's nice after all this time to be able to lift the bonnet and show the machinery.
All right,
Cool.
so thank you, everyone. And I think we'll switch to Matthew's talk then, right?
Yes.
If
anyone, zero obligations to stay.
No,
please.
I'm interested.
I'm interested.
Please go.
Me too.
Yeah. Let's just start a timer. Okay. Can you unshare your screen, Philip?
Yes, sorry.
Presentation. Okay, so I'm now going to talk about how you actually design a very large scale system or large scale libraries using this stuff. This is purely a view from Agda. So if people do have solutions, people who are experts in other theorem proving systems do have solutions to these problems that I'm going to raise, please shout out. We'd be very interested to learn about them. Yeah. Anyway, so I don't think I need to, well, maybe. That's okay. So Agda is a dependently typed language, interactive to improver, and it's a programming language. So, I mean, we've been showing how you can prove stuff in it. It's been used to prove hardware, software, programming languages, mathematics. But people have also written real programs in inverted commas. People have written a compiler, fully functioning compiler in it for a language called CD. and people have written GUIs in it. I'm not quite sure why they would, but I personally think they're insane, but they have. So the Agda standard library has got to support all of these, and it's got to be, all things for all people. It's pretty huge. It's by dependently typed development standards. It's 110,000 lines of code over about 1,000 files. And to type check it all at the same time takes about 4.5 gigs of RAM, and there's about 110 contributors. So it really is quite a large development. And this has raised all sorts of design decisions, interesting design decisions about how you actually design something at this scale that, with dependent types that scales nicely and supports everything that these different use cases want. One of the big problems actually that we have is dependencies between modules in the Agda standard library. This may not be that surprising. Dependencies in, between software packages is always known to be a huge problem. But this, for example, is a dependency graph for the module data.rational.properties, which is, as you might imagine, is properties over rational numbers. And this is after 5 years of work of trying to cut down the number of dependencies that every module has. As you can see, it's a pretty hideous and labyrinthine. Hard to, you could inspect it, but it's hard to understand. So there's a reason why people may dislike importing modules that depend on a lot of other modules. And one of them, the first one, is that they might be philosophically opposed to it. If you have a proof of a proof of something, then you don't want it to depend on, you don't want to have to type check a whole load of completely unrelated proofs. And because you might have, this has its practical consequences too, because you might end up accidentally depending on proofs that you don't want to. You could be mathematically opposed to it. For example, some modules might use axioms built into Agda that you don't want to support, that aren't used in your mathematical model. So for a classic example of this is if you're working in univalence land, then you don't want to use modules in Agda that use the K axiom. The problem is if you have a standard library module that does use the K axiom, then that's going to, and you depend on it, then that's going to pollute all your proofs, because even if you don't use anything that uses the K axiom in that module, Agda still thinks that the K axiom is being used in your proof. Another more practical issue is that it may increase the time required to type check. It takes about 8 or 9 minutes to type check the entire library. If your boot up time, it's a minor thing, but if you pull in large proportions of the library, then taking up the time to type check, just to boot up your Agda the first time might take 6-7 minutes, which you don't particularly want. And in particular, memory required to type check. I used to run Agda on a 4 GB machine, and if I accidentally imported the wrong module in the standard library, then my machine would freeze as I ran out of RAM. So you want a small memory footprint as well, so you need small dependencies. So there's lots of pressure to have small files with, that you can pick and mix what you want to import without being forced to import everything. And in the end, I'm not sure if the people who are doing quick maths on the other one can see that on average in the standard library, about 100 lines per file. There's many ways that we go about splitting up dependencies and minimizing dependency cycles, but the big one that I want to talk about today is talking about the split between computation and definitions and proofs. So this is the dependency graph for the rational properties again, and the modules I've highlighted in blue are the actual modules that contain computation in the standard sense. Computation over natural, functions over naturals, functions over rationals, functions over lists, things like that. And how the standard, and one of the use cases for the standard library, right, is partial verification of programs. You don't want to verify your entire program, you just want to verify the important bits of it. For example, if you're writing some actual IO-based program like a compiler, you don't want to verify everything. just some of it, just the important passes. And in the rest of it, where that you don't want to verify, you don't want your dependencies you don't want to depend on all the proofs in the standard library. You just want to be able to import the functions, do the actual computation you need to feed the data in and out of the verified parts of it. So one of the ways in which the standard library splits itself up is that it separates out the computation parts, the modules that focus on type definitions and computation from those that focus on the proofs about those definitions and computation. And if I was more advanced, I'd have a lovely animation of these blue modules sliding out to form their own dependency tree, but I don't. maybe in time for the actual talk. So we have base modules for all the different data types, and we have the properties modules which contain the corresponding properties modules that contain the proofs, and then data.nat will re-export all of data.nat.base and the relevant some of data.nat.properties to provide a nice unified interface for those who just want to import everything all together. So what are some problems with this split? Hopefully this sounds reasonable. What are some problems that emerge from this? Well, let's consider a basic sorting function in Haskell, sort, which assumes it takes type class ord over type A, so that A has some order associated with it, and it takes a list of A's to a list of A's. Now, the problem with this is that it's assuming, the implicit assumption of this function is that the order is total. But this can't be enforced in Haskell because its type system is not up to it. In Agda, one of the main selling points of dependent types, right, is that you can enforce this as a precondition. So you can actually write down the proof of, write down what it means to be a total order, and you can take in, you can require that sort takes in a proof of this. Now, the problem here, right, and this is all well and good, and indeed this is what many examples, when you're reading Agda tutorials, this is the sort of stuff that people write. The problem is that is actually when you come to use this function, because if you've put this in one of your base modules, then to actually use this function, you need to pass it a proof of total ordering, and that proof lives in the property files. So suddenly, if you're enforcing this precondition using these dependent types, then you suddenly start having to rely to use the function. You have to start pulling in large portions of the library again, all the proofs part of the library. So, well, what's the consequence of this? In actual fact, in many parts of the standard library, we don't enforce these preconditions using dependent types. The proofs require the proof of correctness. If you're trying to prove that the output of sort is in an increasing list, then you need the proof requires for it to be a total order, but the actual function itself in the standard library does not require it to be a total order. So we can't seem to enforce preconditions, which is slightly worrying, and we also need to have separate structures for with and without the laws associated with them, which is a bit of a pain. So we can't just define for instance, a monoid or a ring. We also have to define raw monoid and raw ring, which just contain the operations over them, so that the functions themselves can be parameterized by the raw ones, and the proofs can be parameterized by the ones with the laws. What's another consequence? Well, abstraction suffers as well. Hopefully everyone agrees that abstraction barriers are important in software, especially in interactive theorem provers where implementation details matter, really matter, much more than, it's not just observable input-output behavior that matters, as in normal languages, actually implementation matters as well. In Agda, abstraction barriers are enforced via the abstract keyword. You put your definition under the abstract block, and anything outside the abstract block can only see the definition and the type signature of it, but it can't actually look inside Q to see that it has these fields: numerator, denominator, -1 is coprime, etc. Oh my God, 12 minutes is short. Okay, what's the problem? Well, the problem is that we've now moved the proofs about rationals, for example, into a separate file, into data.rational.properties. Now, this means that these proofs can't look inside this definition, and therefore you can't prove things about these rational numbers that you just defined, because the abstract works locally within a file, within a module. If you move into a separate module, then you can no longer look inside of them. So if we want to separate definitions and computation proof, it appears that we can't have abstraction. Well, how can we try and work around this? We could define a new module, data.rational.abstract, say, that redeclares all the base definitions from the base modules and the properties modules underneath the abstract keyword. The problem with this, of course, is that it doesn't scale well. You need to, for every operation and for every proof, you need to redeclare it. It's difficult to maintain long term, because whenever anyone alters anything, you have to alter the abstract module. It still relies on convention, because you haven't actually inserted an abstraction barrier. You've only inserted an abstraction barrier in data.rational.abstract. Users can still access the original data.rational.base. And we've gone back to square one, right? Because this data.rational.abstract doesn't actually minimize dependencies. You can't use the abstract versions of the operations without also depending on all the proofs. So in some sense, we're back to square one with this solution. One tentative proposal might be to extend the power of the abstract keyword in Agda to allow you to allow it to affect opening of modules underneath in an abstract scope. So everything that you publicly exported underneath an abstract keyword would become abstract, and that would solve the scalability and maintainability problems. But again, it doesn't solve the underlying problem, but it still relies on convention, and it still doesn't minimize dependencies. I mean, a true solution, in my opinion, would require some sort of intermodule level access control for both private and abstract, so that you could specify within these modules, you can look within this subtree of modules, it can look within these definitions, but anything outside of this subtree can't. This is very woolly. I don't have a concrete suggestion. People are going to shoot me when I mention this. This is somewhat similar to what the Java 9 module system does. Yes, I've mentioned Java in a functional programming talk. Apologies. So what are the conclusions? Well, dependencies are a big problem in reusable libraries. Our solutions seem to cause almost more problems than they solve. Agda needs better support for abstraction, which is not well understood on a theoretical basis, as I understand. Yeah, thank you all for coming. Oh my God. 12 minutes is ridiculous. How are you supposed to how are you supposed to say anything in 12 minutes?
Well, there are lots of things that you already know how to do, but one of them is say something different from what is written on the slide.
Yeah.
Let the audience do the reading for themselves.
Yeah.
So what you have to do is then have a shorter, punchier, more slogan-driven rah 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 speech to lay over it. Yeah.
I need to cut down on the introduction as well. Yeah. Comments more than welcome.
Yeah, I'll give them offline, Matthew, because I really have to go to another meeting. But great, thanks very much, and best of luck. When's the actual talk?
Next Saturday.
Okay, so there's
ages of time. Yeah.
Yeah, great. Okay, bye everyone. See you soon.
Yeah.
My comment is that the object-oriented community has grappled with this kind of stuff for a long time.
Yes. Yeah. And I think that's because their size of their developments are much larger than the typical size of, and it hasn't reared its head independently typed. languages, because I assume the lean mathlib suffers similar problems, which is by far and away the largest development, I think, which dwarfs the standard library. But I'm not sure what they're up to. They're up to millions of lines. Right now.
Could the two people in the same room mute each other?
I'm sorry, we're getting terrible feedback from someone. Yeah. Sorry, go again, Luca.
I was saying exactly that.
Yeah, and I'm not aware of any dependently typed language, or theorem prover that has these sort of abstraction barriers that I think you need. I mean, the other thought is that maybe we're barking up the wrong. Maybe we've made the wrong choice in the Agda standard library, which is entirely possible, that we shouldn't be separating computation and definitions from proofs, and that they should live. You should have small modules that define a single operation and then all the proofs about them. But then that raises huge other problems on discoverability. It becomes very hard to find things.
You probably need something like mixins also if you do that.
Yeah. And I mean, where do you put the question then becomes, where do you put properties that relate both, greatest common divisor and multiplication and and x and y? Do they live in the multiplication file? Do they live in the greatest common divisor file? Do they live in the
well, you would have to live in a separate file, because otherwise you introduce dependencies between multiplication and right?
Well, yeah.
That's
I mean, this is the thing. So,
but yeah, it's difficult enough for a non-power user of Agda to find things in the standard library as is, I think. So
that's also our thought, is that we're trying to,
maybe things need to be able to, a single compilation unit, a single file needs to actually generate multiple loadable files.
Yes, that's an interesting suggestion. Yeah,
technically,
I mean, so there's
already do that in Java, because in Java you can have multiple classes in a file, and they actually turn into, in a Java source, and they turn into multiple .class files when they're compiled.
Yes, yeah, that's interesting. So there's been a similar suggestion. The other people I've given in practice talk to, there's been a similar suggestion, which it's morally along the same lines, that actually, if you type checking should be more discriminative than on a module, than on a whole module basis. It should only type check definitions that you directly depend on. That it shouldn't type check the entire module. If you depend on it, it should only type check those definitions that are directly in your dependency tree. Performance is probably an issue, and it greatly complicates interface files as well, which are used to cache your results, cache your type checking results.
You need to.
Does it mean you get something like type?
Oh. Sorry.
Yeah. So does it mean you get something like a TypeScript compiler? What they do? They also do type checking based on chasing dependencies, so for interactive use.
Sorry, which compiler is this? I didn't quite. TypeScript. I have to confess I don't know much about TypeScript.
So they use language servers. So they use a language server approach instead of a monolithic system.
Yeah.
And then they need this because you tend to use these things inside IDEs, and then
So they don't. So they type check on it. Type checks specifically on demand rather than.
Yeah. So basically, when you ask for the type of an expression, it will only look at parts that contribute to that. And if you actually, and I think it's even the case when actually you want to compile everything, it will actually do that repeatedly until it kind of converges. But I'm not absolutely sure about that aspect.
Okay.
Because and of course the price they pay is that they're unsound and incomplete. So in that sense, I mean they are sound up to a certain level that they are aware of, it seems, but it's not the kind of soundness that we would find sufficient. But it's mostly because, so for example, they forget a lot of interprocedural checking. So maybe that helps them that they don't have to go back too far. I'm not sure. So for example, if you have a piece of program that type checks, no, that doesn't type check, but you extract a piece of code out into a subroutine, or then it will all of a sudden type check, although it's still just as wrong. But it's the analysis won't see it. Right? So I'm not so sure whether that would affect this, because of course in the case of that's the other way around. You want to be much more precise than you ordinarily are. But I think, I mean, the architecture still, I think there are quite a few compilers nowadays that have this compiled language server and this kind of approach.
Agda has a language server. I mean, there is an Agda language server out there, and it's actually reasonably good. But it doesn't give typing. They haven't solved this problem, but exactly what you're talking about. It doesn't give mouse over typing information, which would be.
But I think you can imagine that if you say, for example, I'm compiling this module, that it will just have an index of where to find all the constituent components, like this total order predicate will just know where to find it and what it needs to find to be able to prove that. Or maybe because it knows it has discharged it already, it doesn't need to recompile it. I'm not so sure how clever the compiler is in terms of smart linking and everything.
I mean, it does it entirely. The Agda one at the moment does it entirely on a module basis, per module basis.
So
the module is the
default.
That's the default unit.
For most languages, it does make sense. But I think in an IDE, like for TypeScript, this is something they didn't want. It's more like.
And as Agda does get more, you're absolutely right. I mean, Agda is not. We're going to be facing more of these problems because as more usability tools get developed for Agda, suddenly, theoretically, the Agda compiler does a lot of, magic stuff on, a theoretical basis and allows you to write really loads of cool things. On an interactive usability level, there are a lot of things left to be desired. And actually the usability is hard to integrate post hoc. And anyway.
Thank you very much.
Yeah.
I'm still trying to figure out why this is harder, let's say, than building a big Haskell system. I mean, in the sense that there you have modules from which you explicitly export something and that you can then implicitly import somewhere else. But then typically people will only import those things they need, and then the compiler can warn you, okay, there's something. Of course, it will warn you that you didn't import something that you actually use. Of course, that's an error, but it might even all the way around to tell you, well, you don't need to import this, or you don't need to import this module anymore because you don't use anything from that. But I'm not sure whether that's, does it matter that these are properties or computational things? I don't see that, why that might matter.
So it matters because the size, but when I said the standard library is big, I meant big in absolute lines of code in terms, and 95% of that is proofs. The actual standard library is remarkably small in terms of computational content. And we don't have, we don't even have, a formally verified, map interface or anything like that. As these things, but the reason why you want to separate out computation from proofs is just because the proofs over the size of dependencies. The minute you start bringing proofs in, you just blow up your dependency graph enormously.
Right.
So on that side of things, Haskell.
So maybe it's a bit like that. I would write Haskell code, but I actually also write the generated code with it. So the proofs is like the generated code for the properties.
Yes. Yeah.
See what I mean?
Yeah. And
of course, these are much larger than, and of course, in a normal program language, you would not dream of doing that. But in the case of Agda, you have to do it to satisfy the compiler, unless you have something like strategies that would allow you to kind of write it out more concisely, because you know that the compiler can figure it out himself, and that would reduce the size of the proof.
Yeah.
So maybe that's something that is needed, and that maybe much of these proofs are actually mundane. That you could say, well, actually, many of these things can actually be handled with some kind of tactical language. I don't use Agda myself.
Well, yes.
I think part of it is, for any given function, you usually have multiple properties. So even if the proofs are short, it doesn't matter whether they are tactics or not. It's just, you take addition and you have how many properties of addition just on its own, right? and then interaction with subtraction, multiplication, and what have you, right? So I think
but you don't use that many of these properties, maybe. But you have to write them because somebody has to write them, and maybe together they only make sense. But if you import them somewhere else because you do something with nets, then you want certain properties, but not necessarily all properties. And then I would think it's like smart linking. And you just need a good indexing system to be able to find only those proofs that are relevant to a particular module, but not the other proofs.
Yeah, no, it's definitely one potential solution.
Yeah. No, it would make sense probably to try to compile only the parts of standard, or type check only the parts of standard library that you actually use. But yeah, infrastructure for that would be tricky, probably.
Well, it would be, yeah, it would require quite fundamental rewriting of how Agda compiler functions. But yes, I mean, that's exactly what this workshop is about. It's trying to come up with these, issues and solutions to try and influence other people who write these dependently typed systems.
Yep.
Not that I do, I should say, is that I know nothing about the internals of Agda. I am purely the maintainer of the standard library. So yeah. Just raising problems for other people to try and fix.
Matthew, good luck next week. Sorry, I'm switching off because I think you have an echo from me.
Yeah. Cool. Yeah. Thank you for coming, everyone. And yeah, have a good week.
Thanks for the talk, and thanks everyone for the Agda session. And yeah, take care.
Yes.
Thanks a lot. Bye. Bye.